Rationale for CIC Fittings. Lesson 18. The first commercially available deep canal hearing instrument or completely in the canal hearing aid, CIC, was introduced to the European market in 1991 and 5 years later made up 12% of all hearing aids sold in the United States during the time that CICs have been available for fitting. Manufacturers, hearing instrument practitioners, and consumers have gained considerable knowledge regarding this small and popular form of amplification. CIC fittings provide patients with unique advantages while compelling the hearing instrument practitioner to alter their fitting procedures and validation methods slightly. Advantages of CIC fittings. Reduction of the occlusion effect. When a person speaks or moves their jaw, the ear canal walls within the cartilaginous portion of the ear canal change shape, setting air particles in motion. Within the ear canal, without a hearing aid in the ear, the air particles are channeled out of the canal. With an aid in place, they are forced to flow inward, resulting in the perception of the patient's own voice being louder, scratchy, and unpleasant. This effect has been termed the occlusion effect, and due to the increase in bone-conducted sound for frequencies below 2000 Hz, when the external ear or ear canal is covered, it has been long believed that when an earplug is inserted more deeply into the inner bony 1/3 of the external ear canal, it reduces the occlusion effect, providing an alternative to the traditional form of occlusion effect reduction, which is increased venting. The amount of occlusion effect reduction varies by patient and by CIC, but overall, patients' voices should be rendered more natural with CIC fittings. Increase in high-frequency emphasis. The microphone, by definition of the aid being a CIC, must fit down into the ear canal. This deeper placed microphone disrupts the ear's own natural resonance less than other forms of amplification, allowing for a greater retention of the ear's ability to transmit sounds between 2000 and 4000 Hz more efficiently. Both the primary resonance at around 2700 Hz can be preserved to some degree, as with the secondary resonant peak of 4000 to 5000 Hz. This allows for increased high-frequency amplification without placing additional demands upon the hearing aid circuit. The following figure demonstrates via real ear insertion gain the increased high-frequency gain associated with CICs when compared to other forms of amplification. Gain reduction. As CICs fit closer to the tympanic membrane and the residual cavity between the tip of the ear canal and the eardrum is smaller, less gain is required from the hearing aid to provide the same amount of amplification to the patient. While this seems impossible, it is similar to placing the same radio at the same volume into a very small room such as a closet versus a very large room such as an auditorium. The radio will sound louder in the closet than in the auditorium, even though the sound is equally loud. Since a prescribed amount of amplification is required based upon the hearing loss, the cavity is smaller. The hearing aid can provide less gain to sound equally loud. This allows for greater degrees of hearing loss to be fit with the same gain circuits and for patients to use less gain with their instruments, which has advantages in reducing feedback and increasing battery life. Reduction in feedback. Typically, CICs provide very small pressure, equalization venting, or no venting at all. with venting one of the major sources of chronic feedback with hearing aids. In addition, as has been mentioned, less gain is required for CIC fittings. Finally, CIC fittings are usually more tightly fitting than other forms of amplification. These three variables provide for a reduction in feedback for patients. Undistorted output. A benefit of using less gain is the ability to have an increase in output that is distortion-free or increased headroom. Headroom describes the condition that occurs when the input plus the gain of the hearing aid does not exceed the SSPL 90 of the hearing aid. Once the SSPL 90 of the hearing aid is exceeded, the hearing aid is said to be in saturation and distorting. If we suppose that a patient is in an environment which is 70 dB SPL and the CIC hearing aid that the patient is wearing only requires 15 dB gain, the total output equals 85 dB, which is underneath the SSPL 90. Value associated with distortion. However, should the same patient require the use of another style of hearing aid with 30 dB of amplification to meet their gain requirements, the 30 dB SPL added to the 70 dB SPL environmental condition will force their hearing aid into saturation, as the output of 100 dB SPL would exceed the upper level of their hearing aid. Miscellaneous advantages. Due to the deeper microphone placement, CICs have been found to have a decrease in wind noise, while the wind noise was found to be reduced by 7 dB SPL when compared to ITE fittings for wind coming from all directions. When the wind was coming from directly ahead, the CIC offered 23 dB less wind noise. Telephone use is facilitated when using CICs due to the reduction of feedback with a deeper microphone placement. Additionally, the use of stethoscopes and headsets are facilitated for the same reason. Some researchers have reported an increase in intelligibility in noise with CICs that is presumably due to creating a large real ear occluded response or creating the maximum earplug effect with the hearing aid in but not turned on, which attenuates the response of the hearing aid over a wide range of frequencies. This attenuation lessens the level of background noise, improving signal-to-noise ratio. Essentially, the hearing aid acts as an earplug, and then only those frequencies that are required for speech are amplified. Miscellaneous disadvantages. It would not be fitting to list advantages of CIC fittings without describing disadvantages as well. Fortunately, the advantages outweigh the disadvantages, but several disadvantages still remain. While feedback reduction was listed as an advantage, it must be listed as a disadvantage as well. Chronic feedback due to mandibular joint movement plagues some patients. Manufacturers have various suggestions for reducing this phenomenon, but even after following the manufacturer guidelines, some patients are not successfully fit or are fit in the office, but the hearing aid works itself out of the ear when chewing or talking. canal locks, open jaw impressions, or built-up rings, spirals, of soft hard materials, but are a few of the suggestions manufacturers have for reducing this problem. Due to size limitations, the patient's ability to manipulate the hearing aid is severely limited. Many CICs are fit without volume controls and without dispenser or patient controls. This lack of fitting flexibility has been reduced with the introduction of programmable CICs, but many CICs still have less fitting flexibility than their larger counterparts. Cost is also a current limitation. Cost is also a current limitation. CICs have a higher percentage of returns and are more difficult for manufacturers to produce, so costs remain higher for these similar instruments. Smaller instruments. Fitting procedure alteration. The following are general suggestions for alteration of traditional fitting procedure. It should be noted that each manufacturer has unique suggestions for alteration, and the manufacturer of choice should be contacted to ensure that their procedures are carried out when taking impressions, ordering a circuit, or prescribing a material. Impression techniques. While a satisfactory impression is critical for all hearing aid orders, with CICs the impression process becomes even more critical. An adequately long ear impression is imperative. At least 2 millimeters beyond the second bend is mandatory to ensure appropriate sound direction and canal direction. Silicone impression material is strongly recommended for CIC impressions, as it is less likely to stretch when being removed from the ear canal. Medium viscosity materials are recommended both for patient comfort and the degree that they remain true to the ear canal shape. Special ear blocks are recommended. This can vary from oiled cotton blocks, which take up less room in the ear canal, than foam blocks, while providing a stable barrier to the impression material, to vented blocks, which allow for air equalization, to special blocks provided by the manufacturer. The mandible plays a unique role with CIC fittings, and consequently, due to the different shaped impressions obtained from different jaw positions, some manufacturers recommend taking an open jaw impression, while others recommend having the patient remain quiet or chewing/talking while taking an impression of the patient's ear. Circuit selection. The frequency response of the CIC will vary from that of other forms of amplification for a variety of reasons. Using a prescriptive formula for gain that has not been altered for CIC fittings will result in the CIC being too strong or loud. CIC corrections must be used to ensure that the gain expected in the ear canal is obtained, as the hearing aid is being placed into a cavity much smaller than the ANSI 2cc coupler typically used. For verification, the gain values obtained from the manufacturer will appear weaker than expected. When making measurements in the office, either a smaller CIC coupler must be used to more adequately predict the gain in the ear canal, or correction factors should be employed. The slope of the CIC hearing aid must often be a flatter for patients than would be anticipated, providing an increase in low-frequency amplification. This is particularly true if the patient has normal low-frequency hearing acuity. The small pinhole vent and tight fit of CICs does not allow for low-frequency transfer of sound information, as is the case for other types of amplification. Without this low-frequency information, the patient will report that they do not hear as well with their hearing aid as without it. And when tested, the patients will demonstrate a low-frequency hearing loss with the hearing aid in. The hearing aid is essentially acting as an earplug. By increasing the low-frequency emphasis of the circuit, his problem is eliminated. It has been previously mentioned, the deep microphone placement of a CIC hearing aid allows for a natural retention of high-frequency emphasis at 2700 to 4000 Hertz. This retention must be taken into consideration when prescribing the amount of high-frequency gain required to avoid over-amplification and a shrill, harsh sound quality. A reduction in high-frequency gain provided by the instrument will allow for fitting criteria to be met. With instruments that do not have volume controls that allow patients to limit amplification upon demand, increased attention must be placed on circuits that allow for automatic gain reduction in loud environments. Many such circuits allow for patients to comfortably wear their hearing aids without being dependent upon a volume control. Manufacturing methods. Many CIC hearing aids are produced using different shell materials and designs than their larger counterparts. These shell materials, such as ultraviolet shells, often require additional skills for modification as well as other types of material equipment for in-office patching, building up or buffing. Materials and methods vary from manufacturer to manufacturer, but it is imperative that the materials used for modification be compatible with the manufacturer being used for hearing aid production. Validation methods. Real ear measurement. REM. With traditional real measurement, it is recommended that the probe be placed at least 4 millimeters beyond the tip of the hearing aid in order to avoid transitional field or evanescent wave artifacts in the higher frequency range. In addition, it is recommended that the tip of the probe be placed within 5 millimeters of the eardrum to avoid standing waves. Finally, due to the low frequency transfer of energy through the acoustic vent, it is never recommended that the probe be inserted through the vent. With CIC fittings, only the middle statement of the above three statements remains true. The probe should be within 5 millimeters of the eardrum to avoid standing waves, but provided the tip extends beyond the end of the ear canal of the CIC, no appreciable difference in frequency response will be obtained. As feedback with CIC fittings with a probe in place often creates problems with real ear measurements, the probe can be inserted through the vent. The vent of a CIC does not allow for significant acoustic transfer of low-frequency information, so placing the probe through the vent or alongside the aid will provide virtually the same information. Functional gain under headphones. Functional gain allows us to compare unaided results with aided results, and are usually obtained using sound field stimulation. Sound field stimulation has distinct advantages due to the retest reliability with patient head movement and the inability to test each ear independently. With CIC fittings, just as most patients are able to use the telephone, a stethoscope, or headset, functional gain measurements can be obtained under headphones. The advantage of this form of functional gain testing is that it has less test-retest variability and allows for each ear to be assessed independently. In addition, it is simple for the patient to understand and appreciate the improvement between unaided and aided thresholds. An audiogram, such as the one in Figure 18.3, could easily demonstrate the improvement in threshold via this method. However, functional gain is more time-consuming and less comprehensive than real ear measurement.